Hi guys, it's Steven here again. Today I'm going to be talking about Chapter 10, which is Covariance and Correlation. So Chapter 10 is broken up into three sections. The first section is Expectation and Joint Distributions. Section 2 is on covariance, and Section 3 is on the correlation coefficient. And as always, the textbook we're using for the course is A Modern Introduction to Probability and Statistics. So before getting into the material, I wanted to talk about why is chapter 10 important. So events are often connected to other events. We saw this before with conditional probability, and this is sort of a different form of conditional probability, and we're not necessarily calculating a probability anymore, but more so a different representation of measuring the relationship between two variables. So for example, we could be looking at blood pressure and heart attacks. The connection between blood pressure and heart attacks could be that when someone has a higher blood pressure, they're more likely to get a heart attack. Another example would be player performance and game outcomes. When a player has a good performance when they're playing whichever sport, say basketball for example, when they score a lot of points, there's a higher chance or there's a higher probability that they're going to win the game. So having a higher score increases the game outcome. Another example would be the amount of precipitation and the length of a bike ride. So when it's raining a lot outside, the length of your bike ride is probably going to go down. So when rain goes up, the length of your bike ride goes down, and this would be called like a negative correlation or a negative covariance. So chapter 10 helps us to determine and compare relationships between variables. It gives us a measurement, a way to measure these relationships. And it is very important, or these relationships is very important for modeling when you're trying to, or for statistical modeling when you're trying to make predictions. But I'm not sure how in depth you guys will go in this course, but it's definitely important in future courses. And so chapter 10 is important for success in this course and in future courses as well. All right, so let's start with an example. So consider a farmer who wants to create a rectangular plot to plant potatoes. If the width of the plot will be between 5 and 10 meters, and the length of the plot will be between 10 and 15 meters, what is the expected area of the plot, assuming both width and length are chosen from uniform distributions? So think about that for a second. Whenever you get a word problem, it's important to try and dissect the information and write out what you know. And usually this consists of having some let statements. We can see we don't really have any variables here. We probably want to introduce some variables. So we're looking at a rectangular plot, right, which has a width between 5 and 10, a length between 10 and 15, and we want the expected area, right? So area, length, and width, that sounds like we have some material that we need, right? There might be an equation that we can use to link that together. And we know that the length and width are chosen from uniform distributions, which is important when we need to consider how the distribution between 5 and 10 looks and 10 and 15. All right, so we have let A be the area of the plot, and we want the expected value of A, right? So I have a let statement here. I'm going to try and introduce some more let statements on the next page for width and length. All right, so we have width should be, okay, sorry, so width should be between 10 and should be between 5 and 10, and length should be between 10 and 15. I will make sure to fix that for the slides that I post, and we can see here it's adapted. All right, so we're going to let L be the length of the plot, right? We know that L follows a uniform distribution. It's going to be 10 and 15. And then let W be the width of the plot. I know that W follows a uniform distribution between 5 and 10. And we want the expected value of the area. All right, so we can use the formula for area, which is A is equal to length times width, to help us out here. So we have that the expected value of length times width is equal to, we have the formula for expected value, right? So we can just plug in the formula. I'm going to explain to you the parts of it, right? So we have length times width times this f of L comma W. And this here is called the joint probability density function. And so again, just like the regular probability density function for a single variable, this can be used as a tool to calculate probabilities such as expectations or even the joint CDF or cumulative distribution function. All right. So we want to integrate over all of W, and the function that we're using inside the expectation is L times W, and that's why we have that here. All right, so since length and width are independent, the joint distribution is actually equal to the product of the marginal probability density functions. So we have this right here. And this is very similar to probabilities in general, right? You know how I said that the joint probability density function, just like the probability density function for a single random variable, behaves very similar to a probability. And that's what we can see here. Because it's independent, the joint function is just equal to the product of the marginals. And so we have the expected value of length times width is equal to, now because they're independent, we can break up the integral into two parts. And if this is new to you or does not make sense, please refer back to the calculus review video that I made. All right, so we have W times FW dW. Well, this right here is just equal to the expected value of W, and this right here is equal to the expected value of L. All right, so let's see how we compute it. So just continuing with the computation. If you recognize that this was the expected value of L, you could have just substituted it in here. If you recognize this was the expected value of W, you could have substituted that in here as well. But if we carry through the computation, we get that the answer is 93.75. Let me just double check that really quick. So the expected value of W is going to be 7.5, and the expected value of L is going to be 12.5. And if we multiply that together, we get 93.75, which is perfect. All right, so let's now look at a more formal definition. So for two-dimensional change of variable formula, we have let x and y be random variables, and let g be a function that maps from r squared to r be a function. If x and y are discrete random variables with values a1, a2, and all the way up to as many a's as you need, and b1, b2 going up to as many b's as are in the domain, then the expected value of gxy is equal to the summation over all I times and the summation over all j of gai bj times the probability that x equals ai and y equals bj. So this is kind of, well, very similar to what we just did, except this is for a discrete random variable, whereas we were working with a continuous random variable. So here we have continuous random variable. If x and y are continuous random variables with joint probability density function f, then the expected value of g of x, y is equal to the integral from negative infinity to infinity times, and then the integral from negative infinity to infinity over x and y times g of xy times f of xy dx dy. So this right here is exactly what we did, except now our function, instead of being a generic g of xy, it was x times y, right? Where x was the length and y was the width. So now we have a tool to calculate an expectation of a value that depends on two random variables. So we previously had seen one random variable, now we have two. And in fact, if we wanted to extrapolate this to 3 or more random variables, it would be the exact same process. All right, so if we go back to our example, we can break it into the expectation of L times W. That was our G of XY. This is our function of L and W. And we're integrating over L, integrating over W, and we have L times W times this joint probability density function, and then dl dw. So f of LW is called the joint probability density function. All right, so for a single random variable, we had the linearity of expectations. But does this also hold for joint random variables, or if you had 2 random variables inside the expectation? So let's take a look and let's try to manipulate this as best as we can and see what happens. So we're going to consider 2 continuous random variables, x and y. And there's actually an example in the textbook on, I think, page 137 that talks about discrete random variables in a very similar instance. So, all right, so we have that the expected value of Rx plus Sy plus T is equal to the expected value of Rx plus Sy plus T. And the reason we can do this, just like with the single random variable, is we could actually replace the random variable Rx plus Sy with W, because that is also a random variable, right? The distribution, I'm not really sure what the distribution would be because I don't know what the distribution of x and w, but because we created that formula for any random variable, we can actually use that here as well. All right, so now we just need to solve this integral, and we can just add t here, right? So if we expand this if we expand this portion out inside the integral into x f x y, and we can bring our r factored out, and then we add s, and then we take the integral of y f x y dx dy. Well, now this kind of looks like the expectation of y, right? Except instead of having the probability density function of y, we have the joint probability density function. And this also looks like the expectation of x, but it's not quite because we have a joint probability density function instead of the marginal. So what we can do by using the Bayes or the multiplication rule, which is another form of Bayes rule, we have that the joint distribution is equal to the product of the conditional distribution times the marginal distribution. And now, because we have this this conditional distribution, we can integrate over y, because this is the only function that has y in it. So we can integrate over y first, right? And once we integrate over y first, if we're integrating from negative infinity to infinity, so all possible y values on a conditional probability, it has to sum to 1. And to help you, I guess, reason about that, this is just some probability density function of a variable, right? Given that x is fixed, we could just consider x to be a constant in this case. And so because we're looking at the probability density function of a variable, if we sum over all the possible domain values, it has to equal 1. All right, and that's the definition of a probability density function, right? So this equals 1, that cancels out, and we can do the same thing for the right or the next term. We can now condition on y instead of x, integrate over x here, and this becomes 1. So now we just have the expected value, or the formula for the expected value y, and the formula for the expected value of x. All right, and so this now is good because intuitively we would have thought that this would be the case. So it's good that our intuition was right. All right, so that brings us to the linearity of expectations, and this is on page 137. So the linearity of expectations states that for all numbers r, s, and t, and random variables x and y, we have that the expected value of Rx plus Sy plus t is equal to R times the expected value of x plus S times the expected value of y plus t. So that's really nice because now whenever we have a linear combination of random variables, we can break it up into their individual expectations, which if we know the distribution of x and y, we can just solve it. That'll allow us to solve this this more complex expectation. All right, so section 2 is on covariance. And before getting into exactly what covariance is, if we have this expression right here, which says that the expected value of Rx plus Sy plus t, this is equal to R times the expected value of x plus S times the expected value of y plus t. This is the linearity of expectation for multiple variables. What about the variance of multiple variables, or the variance of this linear combination, right? Does it equal R squared times Vx plus S squared times Vy? What do you think? So intuitively, you might think that it makes sense because the expected value has this linear property. Variance is kind of different, but we remember with the single variable, we just took out the R squared, and it's like kind of worked. So let's take a look, and let's use the definition of variance to see if it'll help us out. So since t is a constant, we can remove the t, and we can do that with the same logic we did earlier if we replaced Rx plus SW with, plus Sy with, say, a random variable W. All right, so by definition, the variance of Rx plus Sy is equal to the expected value of, and please forgive me for these unaligned equals. I could not get it to align, but hopefully it doesn't affect the readability too much. All right, so by definition, we have the expected value of Rx plus Sy all squared minus the expected value of Rx plus Sy and the expectation squared. All right, and so this is equal to, we can expand the first term, and that gives us R squared x squared plus 2rs xy plus R squared y squared. And now the second term, we can use our linearity of expectations, which we know. And this gives us R times the expected value of x plus S times the expected value of y, and this is all squared, right? So now we can apply the linearity of expectations to the first term. And then to the second term, we can expand this, this binomial. So we have R squared. So we have R squared expected value of x squared plus 2rs expected value of xy plus S squared expected value of y squared minus all of this. R squared expected value of x squared plus 2rs expected value of x times expected value of y plus S squared expected value of y squared. All right, and now if we group like terms, right? So if we look at the coefficients for R squared, we have expected value of x squared minus expected value of x squared plus 2rs expected value of xy minus expected value of x times expected value of y plus S squared times expected value of y squared minus expected value of y squared. And now we know that this, well, that's the equation for variance of x. And we know that this is the equation for the variance of y, or the formula. But what about this term right here? We cannot take the expected value of x, y and make it the expected value of x times the expected value of y. Yeah, so if it was independent, then we would be able to do that if x and y were independent, but we don't know any information about x and y aside from the fact that they are random variables. All right, so we have R squared variance of x plus S squared variance of y plus 2rs expected value of xy expected value of x minus expected value of y, right? All right, so this is what we thought the answer was going to be, right? Or what we were asking ourselves, right? Like intuitively, okay, you're adding this together. If we use the linearity property for variance, maybe we get something like this. But unfortunately, there's also this term right here. And so what is this last term? All right, let's take a look at what this is. All right, so now let's get into a definition. So a definition of covariance. So we have let x and y be two random variables. So the definition of a covariance, or the covariance between x and y, is defined by covariance of x and y is equal to the expected value of x minus expected value of x times y minus the expected value of y. All right, so that's interesting, and that's definitely something to think about. But let's look at this alternate expression for the covariance. And we can get this alternate expression by expanding these binomials together and then taking the linearity of expectation. And if you don't believe me, I highly recommend doing it yourself, because this is it's just another opportunity to practice your algebraic manipulation. But you should get an equation that looks like this. And so now we have covariance of xy is equal to expected value of xy minus the expected value of x times the expected value of y. All right, now this looks familiar, right? We just encountered this term on the last slide, and it was right here, right? So now we can actually substitute that value in. Okay, I think we're going to substitute in later, but we would just be able to substitute that in here, and then we'd get r squared variance of x plus s squared variance of y plus 2rs covariance of xy. All right, we don't know a lot about the covariance yet, but I'm going to talk about it, so don't worry. All right, so why is covariance important? All right, so here's the definition, and I'm going to stick with this definition to make a brief explanation here. So when we're looking at the definition, let's consider the terms in this expectation. It looks kind of complex, but let me try to break it down for you. So we are looking at the expected value of the product between x minus its mean and y minus its mean, right? Because the mean is the expected value. They're synonyms. If you haven't realized that by now, then hopefully now you know. So we have x minus its mean, right? So we have all our x values, or all the possible outcomes of x, and we're subtracting the mean of x, right? So in a way, we're kind of like centering the data, right? So for example, if you had like a glass of water, but you already knew that the glass of water would have at least 100 milliliters at the bottom, well, we could just subtract off the 100 milliliters of water and still know about and still consider the variation of water. So that might not have been the best example, but let me keep talking and hopefully it'll make more sense. So we have x minus its mean and we have y minus its mean. So if the covariance of xy, which is this expression right here, is greater than 0, how could it be greater than 0? What would that tell us? Well, that would mean that on average, right? Because expectation, when you're looking at expectation, you're looking about the average, right? On average, when x is larger than its mean, right? That would mean that x minus expected value of x is positive, right? Then y is larger than its mean as well. All right, so how did I get that? Well, all right, so looking at to see whether the covariance is positive or negative it's just a simple attribute, right? But in order for the covariance to be positive, both of these terms need to be positive, right? Because if on average x minus the expected value of x was positive, but y minus the expected value of y is negative, then they would not be correlated together, right? Or it wouldn't be positive, because if this is positive and this is negative, then on average it's going to be negative, right? And so the covariance would not be greater than 0. So when x is larger than its mean, y is larger than its mean. But what does this also mean? Because if x was less than its mean, right, we would have that x minus the expected value of x is negative. And if y was also less than its mean when x was less than its mean, then we'd have y minus the expected value of y is also negative. So that would become a positive covariance. So another way to interpret this is that when when x is less than its mean, y is also less than its mean as well. So in this case, we say that x and y are positively correlated. And the reason we're using positive here is because we're looking at covariance greater than 0. And yeah, so they could either be positive correlated if when one is negative, the other is negative, or when one is positive, the other is positive. And I mean that with respect to their means. All right, similarly, if the covariance of xy is less than 0, then on average, when x is larger, y is smaller, right? And what that means is that when x is larger than its mean, I should have than its mean here, but when x is larger than its mean, that means that x minus expected value of x is positive, and then we have y minus expected value of y should be negative because the covariance is less than 0. So in this case, we say that x and y are negatively correlated. Excuse me. So why is this important? This whole idea of like correlation, we're saying like positively correlated, negatively correlated. Well, if we know that two variables are negatively correlated or positively correlated, then knowing the value of one variable will might give us information about the value of another variable. So for example, there's a lot of studies out there that talk about the correlation between smoking and lung cancer, right? And the correlation is very positive between, like, you might hear that the correlation between smoking and cancer is positive, right? And what that means is that the more you smoke, the higher probability of getting cancer. The higher the probability of getting cancer. Because the chance of getting cancer goes up, or as you smoke goes up, the probability or the chance of getting cancer goes up, right? Because they're positively correlated. But you might see studies that say if you don't smoke or if you exercise, then the probability of getting cancer goes down. And so exercise would be like your X in this case, right? So the more you exercise, then and by more, it means more than the average person, right? If you exercise more than the average person, then the chances of you getting cancer is less than the average person, right? Than the expected value. So in this case, you would say that exercise and cancer are actually negatively correlated. And that makes sense, right? You wouldn't think that exercising more would increase your chance of cancer. Of course, it might. I don't know. There could be studies out there, but I highly doubt it. But yeah, so that's just an example of a negatively and positively correlated variables. And so obviously that's important. You guys have heard about these terms, and now you can understand where they're coming from. All right, so the other thing I wanted to point out is, I'm sure you noticed this, it's called covariance, right? You guys have heard of a word similar to covariance, and that's variance, right? So covariance and variance, some people get this mixed up. Actually, a lot of people do. So if you do, don't get too mad at yourself. But this is the time that we can clear this up, right? And if you're still confused after this slide or after this entire tutorial, please send me an email, come to office hours, post a question on Piazza. All right. So variance, when we're looking at variance, we're looking at a single random variable, right? Or we're looking at the variability of a single random variable, right? So here we have the variance of x, of random variable x, is the number variance of x is equal to the expected value of x minus the expected value of x squared, right? So it's giving us information about, if we just look at one variable, how much did the values of that variable vary, right? What is the spread? What does the spread kind of look like, right? All right, so, and then we have the alternate expression, which hopefully you guys are very familiar with. Yeah, everybody used this on quiz number 3, which I marked, so I know you guys know this one very well. So we have variance of x is equal to expected value of x squared minus the expected value of x squared. All right, so if we look at just the first definition and we look at the first definition of covariance. So now covariance, we're looking at two random variables, right, instead of one. And we have, instead of having x minus expected value of x squared, we have x minus the expected value of x times y minus the expected value of y. All right, so we're actually looking at, instead of using the same binomial or the same like two-term term squared, we have one of x and one of y. So they're very similar, right? So we're looking at how do the variables vary together, right? If they're positively correlated, then the variance would be, well, their variance is very similar, right? They both vary in like a similar way. But if the correlation is negative, then they don't vary in that similar way, right? They're varying in opposite directions, actually. So now let's look at the alternate expression for variance. So we have, for any random variable, we have variance of x equal to expected value of x squared minus expected value of x squared. And then we have covariance of xy is equal to the expected value of xy minus expected value of x times expected value of y. All right, so here we have x squared, but now instead of having x, two factors of x, we have xy. And then now instead of having expected value of x times expected value of x, we have expected value of x times expected value of y. So we're looking at the variance between two variables instead of the variance within one variable. Okay, so hopefully that makes sense. It's important to recognize the similarity between the both of the expressions. In fact, if you were looking at the covariance between x and x, so x with itself, and you substituted x in for y, you would get the variance of x, right? So because if this y became an x, this would be x squared. If this y became an x, then this would be expected value of x squared, right? So the equations are very tightly connected. And if you still are kind of confused or you wanted to see some more examples, please refer to the pages where they talk about these equations. So that'd be page 96, 97, and 139. All right, so naturally, when we're looking at two variables, like we want to know like if they're independent or dependent on each other, because whenever they're independent, I mean, you guys know it's always like a special kind of case. And we always need to factor in if they are not independent of each other, right? So I pulled this directly from page 140 of your textbook. They just had a really good explanation here. So let's go through it. So independent versus uncorrelated, all right? And I think this is a common thing that a lot of people like to investigate. So now, if we let x and y be two independent random variables, one expects that x and y are uncorrelated. They have nothing to do with another, right? So this is indeed the case. If x and y are discrete, one finds that the expected value of xy, right? We can now calculate that out here using this, just the definition, right? And if they're independent, then we know that the joint distribution is equal to the product of the marginals, right? And if we're only summing over, we're summing over all the I indices here, we can separate that because I and j are both separated. And so now we have summation I probability of xi equals ai, and we have summation of bj probability of y equals bj, and that's expected value of x times expected value of y. So we can actually make this. And I briefly mentioned it earlier when we were talking about when we're trying to derive the linearity to see how linearity is affected in variance, or how variance affects linearity. So we can see here, so if expected value of xy equals expected value of x times expected value of y, then if the definition of covariance, which we just saw, is equal to expected value of xy minus expected value of x times expected value of y, that is equal to 0. And when the covariance is equal to 0, we say that two variables, x and y, are uncorrelated. So If two random variables x and y are independent, then they're uncorrelated. Oh, sorry. A similar reason holds that in case x and y are continuous random variables, yes. So if they're continuous, it's a very similar approach to how we solved the continuous sum linearity property for continuous random variables. So this is important. Independent versus uncorrelated. If two random variables x and y are independent, then x and y are uncorrelated. However, the reverse is not true. If x and y are uncorrelated, they can still be dependent. And the reason where this comes from is that if x and y are uncorrelated, sorry, if x and y are uncorrelated, all that means is that this equation right here, the expected value of xy minus expected value of x times expected value of y, is equal to 0. That means that they're uncorrelated. But we don't know that the expected value of xy is equal to the expected value, we have that the expected value of xy is equal to the expected value of x times expected value of y, but we don't know that this joint distribution here was equal to the product of the marginals. Okay, so this is where we use the independence, but we don't know if that independence actually holds, or if it just happens that this equation, expected value of xy, is equal to expected value of x times expected value of y, like the numerical value. All right, so section 2, let's go to using the definition, we can revisit the variance that we calculated earlier with expected value of xy minus expected value of x times expected value of y. And now we can substitute our covariance of xy in, right? And here we go. So now we have a definition, the variance of the sum. So let x and y be two random variables, then always variance of x plus y is equal to variance of x plus variance of y plus 2 covariance of xy. And if x and y are uncorrelated, then the variance of x plus y is equal to variance of x plus variance of y. So our intuitive definition only holds if x and y are uncorrelated. So what that means is that this value, or the covariance of xy, is equal to 0. And when that's equal to 0, then these terms cancel out. And we actually showed something a little bit stronger than the variance of the sum because we had these constants out front. But as always, you could have just replaced x with, or rx with, say, w, and sy with v. And once you get variance of x and variance of y, you can pull out the s and r. And it becomes s squared r squared. But it also showed us that if we had covariance of some, we had r and s over here, they actually come out front as coefficients. All right, so section 3 is on the correlation coefficient. And this is very, very tightly related to covariance. In fact, it's actually a covariance with a change in units. So covariance under a change of units on page 141, it states that let x and y be two random variables, then the covariance of xy plus, of rx plus s and ty plus u is equal to rt times the covariance of xy for all numbers r, s, t, and u. So in this case, if x is, say, 1 unit, right, and we want to do a transformation from like liters to milliliters, for example, then you want to multiply by 1,000, and maybe there's a constant as well. And so for the covariance, the constants disappear and we pull out the two coefficients, r and t. And we saw that earlier with our evaluation of the variance of rx plus sy plus t. All right, so here's the definition of the correlation coefficient. So if x and y are two random variables, then the correlation coefficient, rho, and that's this symbol here, it kind of looks like a p, rho xy is defined to be 0 if variance of x is equal to 0, or y or variance of y is equal to 0. And otherwise, the probability, or sorry, the row of xy, the correlation of xy, is equal to the covariance of xy divided by the square root of the variance of x times the variance of y. All right, so there's kind of a lot to take in here, but if we think about the covariance of xy, so this is like the variance of x and y together, right? Like considering the two, how the two variables change together. And this is considering variance of x is how x is changing, variance of y is how y is changing, right? But remember, we had two y's here, right? Y squared, and we had x squared over here, right? In the equations. And so instead of using the variance, what we want to do is use the standard deviation. So another way to look at this is the standard deviation of x times the standard deviation of y. And if we divide by the standard deviation of x times the standard deviation of y, we're essentially dividing, or we're essentially normalizing this covariance of x and y. So it can be shown that the covariance of x and y is between -1 and 1. It has to be between -1 and 1. And it's because of that reasoning I just told you, where we are normalizing this covariance. So the closer to +1, the stronger the positive correlation, and the closer to -1, the stronger the negative correlation. So the correlation coefficient is unitless. And so your homework may be to answer why. I mean, I kind of already alluded to it, but the way you'd want to show this is that if you were to replace the covariance of, or sorry, if you were to replace x with rx plus s and y with ty plus u, how would that affect the correlation coefficient? So we saw here that it affects the covariance, because obviously the covariance, this is not covariance of xy, this is covariance of xy times rt. But how would that affect the correlation coefficient? And so you should see that it does not affect it, but if you can try to show that, it would be a good exercise for homework. All right, so that is all the information. This is actually a shorter chapter in the textbook, and that's why, like, if you ever have time, I highly recommend reading the textbook, just to get like the full understanding of all of these sections. All right, so let's just do a summary of the material that we covered. So section 1 talks about expectation and joint distributions. That's on page 135. And then we have, so when we're talking about expectation and joint distributions, what this means is that joint distributions have a joint probability density functions, just like single random variables have probability density functions, right? And they also have joint cumulative distribution functions. We didn't talk about that today, but we can calculate those very similarly in the same manner by integrating over the joint probability density function. All right, so we can use the joint PDF to calculate joint expectations. We saw that. When two variables are independent, their joint distribution function is the product of their individual distributions. In other words, the joint distribution is the product of the marginal distributions if the two variables are independent. All right, section 2 was on covariance. This is on page 138. So covariance is like variance between two random variables, right? Covariance helps us measure whether two variables are positively or negatively correlated. One drawback to covariance is that it's not immune, or I don't know if immune is the right word, but it is not invariant to units. So for example, if you're comparing the covariance of milliliters and kilometers, for example, for precipitation and bike ride distance, then if you were to switch milliliters to liters and kilometers to meters, the covariance would be affected. It would affect the value of the covariance. And with that, it's kind of hard to get a sense of like how connected are two variables together. And that takes us to section 3, which is the correlation coefficient. So the correlation coefficient is very useful for determining the relative strength of a correlation between two variables. And it's powerful because it does not depend on the units of these variables. So when we calculate the covariance between two variables, we could get any value from negative infinity to positive infinity, depending on the units of the variable. But when we're calculating the correlation coefficient, the value has to be between -1 and 1. And what's good about this is that we can now compare the correlation between two variables with the correlation between two other variables. So for example, if we wanted to compare the correlation between blood pressure and heart attack and exercise and heart attack, well, then we could compare how strong the correlation is between blood pressure and a heart attack and exercise and a heart attack by using the correlation coefficient, because now all the values will be between -1 and 1. All right, so that is the end of the tutorial. There will be I will post another video on the questions, on the problem set, the solutions to the problem set, but for the, I guess, lesson portion, this is it. If you have any questions, feel free to post on Piazza, send me an email at steven.brock@mail.utoronto.ca, and as always, I have office hours on Wednesdays from 3 to 4 p.m. Eastern Time. I also appreciate any constructive feedback on this tutorial. Always want to make them better so that you guys understand more. And thank you very much, and best of luck with your studies.